Hello students, my name is Shayan Mitro. I am the faculty member of Department of Electronics and Communication Engineering of Greater Kolkata College of Engineering and Management. Today I am going to taking the class of Embedded System, and the lecture is about Unified Modeling Language, and this is the lecture number 38, and the subject code is EC704B. Okay, so let's begin with the lecture. Okay, so as we have discussed about, so we will start with this lecture today with memories. So in memories, in digital simulation, one often needs two model register files, RAMs and ROMs. Memories are modeled in Verilog simply as an array of registers. Each element of the array is known as a word. Each word can be one or more bits. It is important to differentiate between an 1-bit register and one n bit register. Okay, so in register memory 1 bit is 0 to 1023. In memory 1 bit with 1k 1 bit words. In register 70b mem 1 byte 0 to 1023. Memory 1 byte with 1k 8 bit words. Memory 1 bit 255 fetches 1 bit word whose address is 255. Mem 1 byte fetches 1 byte word whose address is 511. Arrays extended after Verilog 2001. In Verilog 1995, only register, integers and time can be declared as array. Array is limited to 1D. In Verilog 2001, arrays of real time and any type of net are allowed. Okay, so 1D array 8 bit into 8 register R bit, where 70 W net, and this is the vector. Register 30 R 4 bit vector, try register 30 row column adder. These are the specific notation. Okay, each notation has its own explanation. Okay, so depending upon, now suppose 1D array is memory 32 bit into 8, so 3D array, and this is a float variables. Okay, so this is a real float array. Okay, let's go to the next slide. Now strings are sequence of 8 ASCII values. So module string are register 8 14 to str var, initial begin, this is hello world, this is hello world, enable, this is the basic relation. The special characters are new line, these are the character, this is for character. If you have to write any character, it is very much similar to C programming. Okay, let's go. Okay, 4 valued logic. Verilog's nets and registers hold 4 valued data. 0 represent a logic 0 or false condition. 1 represent a logic 1 or true condition. Z, output of an undriven tri-state driver, high impedance value. Models case where nothing is setting a where's value. Models when the simulator can't decide the value, uninitialized or unknown logic value. Initial state or registers when a wire is being driven to 0 and 1 simultaneously. Output of a gate with Z inputs. Logic system in Verilog. 4 values we got 0 1. This is for no state. This is represent no state, not case sensitive here. Okay? The logic value X denotes an unknown ambiguous value. The logic value Z denotes an high impedance. So this is important. Primitive have a built-in logic. Okay, the simulators describe 4 value logic. Okay, so now let's describe. Now suppose what we have here is a AND gate. Okay, the first, the 0. Okay, this is 1 and this is a unknown ambiguous value, and this is a high impedance value. Okay, so okay, so for 0 we got 0 values. As each and every time when you put any A or B 0, the all the output value will be zeros. Okay, for A is equal to 0, the B could be any values, or the Y will always be 0. And for 1, depend if the value is 1. Now for 1, the value always the value of output will always be equal to the value of B depending upon V. Okay, so that's how we create or manipulate the logic. Okay, now next one is for, now if we have an unambiguous value, for 0 we'll always have a 0. Okay, now for unambiguous values, each unambiguous value always provide a unambiguous output. Okay, and for high impedance we always the same result will be followed by. Okay, let's go to the next slide. Okay, resolution of contention between drivers. Okay, the value on a wire with multiple drivers in contention may be X. Okay, so same thing will apply it here. Now this is a inverter and this is the buffer, and depending upon that, so if the value of S0 is 0, the output of A will always be propagated to the input of this inverter. Suppose this value of A is X or something, anything that will be propagated depending upon the value of S0. Okay. Okay, so the same thing. Now this is the series of impulses or pulses. Depending upon that we will get the output. Now suppose, now this is S0. Okay, so depending upon the S0, now the value of S0 is 0. Now value of A is this, so the output will get the value X. Depending, now if the value of A is unambiguous, we always get output at output 3 in this inverter, we get the high impedance value. Okay, so now suppose the value of S0 is 1. Okay, so we will get a 0 value. The same here. Now suppose we have a value of 1 here at S0, so depending upon the output, suppose this is the A, so it will be propagated. The same will applicable for high impedance and X. Now for high impedance and the value of unambiguous value, we will always get a, for unambiguous value input we will get a high impedance output. For high impedance input we get a unambiguous output. Okay, so this is the A. This A will propagated to the output port. The same will applicable to each and every inverter. Okay, so this is the AND gate, A and B. Okay, depending upon that we'll get the output. The same will applicable to each and every. This is the OR gate, so all logic will be act according to it. Okay, so let's go to the next slide. Logic strength level. Types of strength: charge strength, tri-resistor, large, medium or small. Drive strength will supply greater than strong, greater than pull, greater than weak, depending upon that. Syntax will be net type, strength, range, delay, variables. The strength levels are high Z, small, medium, weak, large, pull and strong. Apply. Okay, format size, base format and number. Size, decimal specification of number of bits. Default is unsized and machine dependent but at least 32 bits. Base format followed by arithmetic base of number. D, decimal default base if no base format is given. This is for hexadecimal, this is for octal and this is for binary and so on. Number value given base for base format can be used for reading clarity, and a first character of sized binary number is 0x or z will extend to 01x or z defined later. Depending upon the input size we will get the output. This is that what I have discussed in the earlier slides. Okay, let's go to the next slide. The examples of number representations are as follows. We have already know now is nothing but is just suppose this is 16 bit H3AB, so it will be extended here. Same is applicable for that, and this is for also. Okay, let's go to the next slide. Vector concatenation. The vector concatenation will be a easy way to group vectors into a larger vector. Representation meanings: see out sum, see out sum. These are for the same applicable for each and everybody. Okay. Okay, parameter declaration. Parameters are not variables, they are constants, so can be defined as a bit or a vector. Typically parameters are used to specify conditions, states, width of vector, entry number of array and delay. Module where marks out I0, I1 is selective. Parameter width is 2, flag is 1, B1. Output width is 10 out, input width is V0 and V1. Input select, assign out, select equal to flag, V1, V0, end module. Overriding the values of parameters. Module instance parameters value assignment. Cannot skip any parameter assignment even you do not want to reassign it. The order of assign of parameters follows the order of a declaration of parameters in the module. You cannot skip the delay parameter assignment. Okay. This is the, now suppose this is the var one, this is the output, and this is the var max. Okay. Depending upon that we get the output. Okay. You can use definition parameter to group all parameters value override assignment in one module. By using that we can override all the assignments. Okay. Okay. Primitives are: Verilog has predefined logical elements called primitives. Smallest modeling block for simulator. Behavior as software execution in simulator, not hardware description. Verilog built-in primitive gate are AND, OR, NOT, BUF, XOR, NAND, a NOR and XOR. Prime name instance name is output IN0 IN1. User defined primitive are building block defined by designer. Okay, let's go to the next slide. Structural models. Verilog primitive encapsulate predefined functionality of common logic gates. The counterpart of schematic is a structural model composed of Verilog primitives. Model structural detail by instantiating and connecting primitives. primary inputs are these. So it's a basic logic. This logic has been written here. Okay, how it is works now. Take a look. Now this is the module AOI. So we have already assigned it with a str string value. Okay, so y, we assign y as output. This is x as an input. Okay, x in 1, x in 2, x in 3, all the inputs, we assign all the inputs, okay, sequentially, and we get a y output. Okay, so at the very first we create this module block. Okay, you have to remember that the first, before the structure, we have to create the module. Within that module we will create the structure. Okay, so first, this is a very simple logic function here. This is the all the inputs and this is the output. Okay, so all the behavioral, all the modules inputs and outputs will have to be declared first. After that we'll get into the model and we will deduct it step by step. Okay, so next is the next input will be for x in 1 and x in 2. These are the inputs. These are for the port mode. So first we'll declare the modules inputs and then we will declare the port modes. So this is the chip and these are the ports. We have to remember that. So suppose this is the chip. Within that chip, this is the structure behavioral the structural model of the AOI str. Okay, so first we will describe the outer ports and outer values. Okay, so after that we create the where y1 and y2. These are the internal wheres establish connectivity. So this is the y1 and this is the y2. So first you have to declare the modules input output ports. Okay, first the modules, then the output and input as a port modes. Next we have to establish the internal wires, establish connectivity. We have to connect the internal wires. After that we have to instantiate the primitives. Now what is the primitives are? This is the primitives, this is the output. Okay, this is the y1, this is the y2 as the NOR inputs and outputs. And for AND we get y1 x in 1 and x in 2, and for another AND gate we get y2 x in 3, x in 4 and x in 5, and this is the end of the module. Okay, so by this we can structure the whole module or the logical block, could say that. Okay, let's go to the next slide. This is the basic structural model. For this is a very simple structural model, but this is the process, or this is the sequence by which we can establish a structural model of a logic gates, depending on the logic, which logic we are going to create or establish. So the structural connectivity will be wires in Verilog establish connectivity between primitives and or modules. Okay, so now this is the primitives. This is the primitive points. So AND gate, X, NOR, these are the primitives, and this is the structural model. Next, the structural connectivity. Wires in Verilog establish connectivity between primitives and or modules. Data type are the next example wire. The logic value of a wire is determined dynamically during simulation by what is connected to the wire. An undeclared identifier is treated by default as a wire. Use nets to establish structural connectivity. Port connection by name, add half adder, 0 delay M1 for this. For port connection by place, add half adder, delay M1, W1, W2 and AB. Okay, so let's go to the next slide. Hierarchical design examples are model complex structural detail by instantiating modules within the modules. Okay, so this is the point. So suppose this is I would say this is could be a it could be said this is a proper structural model that is going to be described here. Now suppose to create that behavioral model, what we have to do, we have to first initialize first the modules port name and the modules points. So module add, if we have to create add full adder, so delay, this is the sum C, this is the sum, this is the C output point, this is the ABC and C/in point. Okay, so this is the C/in point, this is A, this is B, this is the output and this is the sum. This is for the full adder. Okay, so what we have do, we have used two half adder chip to create a full adder, the module of a full adder. Okay, so these are the inputs. So you will again create that. The output will be this, and which wires we have to create it. After establishing the module port names or port points, we will use the where to establish the connection. So we will again instantiate the modules name, wire names. We have already described or declared the model name and the port name. So after that we establish the wire names. So after that we establish the half adder delay. These are the wire names and the inputs. This is the half adder 0 delay M2 sum W3 C/in and W1, or C/out W2 and W3. This is the end module. Okay, Modeling tip. Use nested module instantiation to create a top-down design hierarchy. Modeling tip. The ports of a module may be listed in any order. The instance name of a module is required. Okay. Let's go to the next slide. Gate and switch level modeling. Coding style. Netlist connect primitives and modules by nets. Primitives. Bottom level of the hierarchy. Verilog gate level primitives. User defined primitives described by the truth table. Conventional modules. Behavioral RTL statements. Structural statements. Switch level modeling using transistors. Verilog built-in primitives. And NAND, OR, NOR, XOR, XNOR. Buffer, NOT, buffer, if 0. These are the Verilog built-in primitives. Okay. These are the ideal MOS switch are for this NMOS, PMOS, CMOS, transistor if 0, transistor if 1. These are the resistive gates RNMOS, RPMOS, RCMOS, RTRAN if 0 and RTRAN if 1. These are the pull up, pull down. Okay. Oh, sorry. Let's go to the next slide. The switch level modeling are two types of MOS switches can be defined with the keywords NMOS and PMOS. NMOS is used to model NMOS transistors. NMOS N1 out data control. PMOS is used to model PMOS transistors and PMOS M1. Okay, so this is the data input, this is the output, this is the control switch of NMOS transistor, this is the control switch of a PMOS transistor. The basic function will be used, functional derivatives will be used for NMOS transistor and PMOS transistor that we have already read earlier. Okay. Okay. Suppose now if you have to discuss how that, now that this is for C and this is for D. Okay. Now when the control gate and the data gate, now when the control gate is 0, we'll always get a high impedance at the output. Okay, always. Now suppose now we take control, we provide the logic 1 at the control gate, so always this data will be passed to the or propagated to the output terminal. Now this is the logic 1. Now the value of data is 0, then 0 will be propagated to the output. Value of data is 1, the value that specific input will propagated to the output. This is high impedance and this is for unambiguous data. Any unambiguous data, anything that appeared at the data point at the data value will propagated to the output depending upon the control switch. Now for PMOS transistor it will be opposite or vice versa, I could say. For control at if the control signal is 0, this 1 will be propagated here. So when control signal value is 0, or any data that is appeared here will propagated to the output port. Other than that, all the values will be we'll say not applicable. Okay. So for high impedance, the unambiguous data of control signal, the for 0 different data will be passed out. Okay. Basically those are not applicable. Okay, let's go. This H stands for 1 or Z and L stands for 0 or Z depending upon the input. Anything could be propagated. Okay, because we don't know the value of the control signal. Okay. Now CMOS switches. The CMOS switches are declared with the keyword CMOS. A CMOS device can be modeled with a NMOS and a PMOS device. So CMOS, now the same process will be taken here. For CMOS C1 out data N control, P control will be created. The CMOS gate is essentially a combination of two gates, one NMOS and one PMOS. For NMOS N1, out data and control will be used, and for PMOS P1, out data and control will be used. So this is the CMOS or complementary MOS. Okay. Now how it works? Now suppose we have provided with, now depending upon these control signals, now what will happen? Now suppose the value, the N control is 1. Okay. So P control will be 0. So data will be propagated through this path. Any data that is appeared here will be propagated to the output port. Now suppose the N control is 0. So vice versa, the value of the P control will be 1. So in each case, any one of the path will be shorted or connected. Connected will be a proper word. Will be connected. So depending upon any value of N control, suppose N control is 0, so value of the P control will be 1, and when value of the N control is 1, the value of P control is 0. So any of this path will always be connected. So each and every time any value of N control for 0 or 1, the data will and always propagated to the output port. So that is the basic function of a CMOS. So that's why it's a much more effective way of using the switch gate. So it could be controlled each and every time. Okay, so only in high impedance state will cut the connection within the data between the path. So only when the both the control signals are on high impedance state, the value of the data will not propagated to the output port. Okay, so let's go to the next slide. Okay, so the next one is a bidirectional switch. The NMOS, PMOS, CMOS gates conduct from drain to source, as we have already known that for depending upon the gate control will create the path, and gate control will create the path, and depending upon the path the data will be propagated. So now it is important to have devices that conduct in both directions. That's very important point. In such cases, signals on either side of the device can be the driver signal. Bidirectional switches are typically used to provide isolation between buses or signals. Now this is the transistor T1 in out and in out. Okay, now if you take a close look, this is the transistor where we have a connection in each case, that each of the data that is appeared in, suppose there is a data in out 2. Now it could be propagated to the in out 1 because there is a path, and the same thing will be applicable to transistor if1, and this is for transistor if0. Now the same will be here. Now for transistor if1, the control logic, when the control logic is 1, the data will be passes from this direction to this direction. Now when the control signal is 0, so the output will now suppose we have a data here, it will not be propagated to the in out 2. The same will be applicable for in out 2 also. Now depending upon, now why is the name of tran if 0? It means when the value of the control signal is 0, the value of in out 1 will be propagated to in out 2, and the value of in out 2 will be propagated to in out 1. Now when the control signal is 1, the data will not be propagated from one port to the another port, or one part to the another part. Okay, this is the basic logic gates that we are have discussed. Okay, and these are the logic gates that will be used for further discussion. Okay, and the power and the ground, that's very important part also. The power is the VDD and logic 1, and ground is VSS and logic 0. Sources are needed when transistor level circuits are designed. Supply 1 are equivalent to VDD in circuits and place a logical 1 on a net. Supply 0 are equivalent to ground or VSS in circuits and place a logical 0 on a net. Supply 1 is for VDD and supply 0 is for GND. Assign A is equal to VDD and assign B is equal to GND. This is connected to a VDD and this is connected to a ground. B will be connected to a ground and A will be connected to the VDD. Power and graduate. Okay. Now the resistive switches have the same syntax as regular switches. Resistive devices have a high source to drain impedance. Regular switches have a low source to drain impedance. Resistive switches reduce signal strengths when signals pass through. Regular switches retain strength levels of signals from input to output. Okay, that's very important point. The input strength are supply, the output strength will be pull, and input strength is strong and output strength will also pull. Input strength is pull and the output strength is weak, and these are the points. For input strength weak, the output strength will be medium, and input strength is large, the output strength will be medium. And when the input strength is medium, the output strength is small, and input strength for small value, the output strength will be small, and these are for high. Okay, let's go to the next slide. Okay, so we will conclude this class here today. In the next lecture, we are going to discuss about the unified modeling language, and we'll end the lecture there. Okay, so thank you.